Coldplay is a machine learning solution to help clinical decision making. Based on FHIR data, which are used as training set, doctors or specialists can enter test group by uploading a file including patient data to tell who would be likely to have diabetes. Our idea is to use a combination of population data and known risk factors to create a likelihood score that a particular patient has diabetes. The application will create an alert if a patient's score is above the provider specified threshold, and it will suggest closer monitoring or testing. We want to achieve automated clinical medical support by providing this lightweight solution, which both decreases the monitoring and time cost of medical care, while increases the convenience and efficiency for diabetes patients. As such, we emphasize on two areas to render this solution. The first one is machine learning. We focus on data training, trying to use a boosted algorithm or code-sensitive learning to deal with unbalanced data set. We also need to automate the diagnosis with a trend classifier. The application can take in patient data and output if the patient may have diabetes or not. This requires that the patient have all of the observations fields that are used in the classifier. For the other part, which is the simple presentation of UI, we focus on considering for all types of users because patients vary in a grade pool. And then we also want to provide easy collection interface to request medical data from targeted users.
Now for a quick demonstration of the Coldplay Clinical Decision Support application. It's a web application, so you would access the application over the internet by browsing to this URL. You would log in using your Facebook account. And that brings you to the main screen, which shows a left navigation pane to the different sections of the application, and the personal dashboard, which is really just a general overview of the patient. It provides basic demographic information about the patient, such as gender, birth date, location, weight, etc. Time was not permitting, but in future releases, the supporting contextual panels could be added to the application to provide more demographic information to support reviewing the patient's information in relation to the population with similar demographics.
Hello, my name is Tim Cordova. I want to cover the document section of our UI application. This basically provides a means to the user to upload their patient information they'd like to classify through the ML algorithm. In this case, it's the FHIR data underscore test that has 10 patient observation values that a user would like to upload. And then the user would take this file, drop it into the UI, and upload it. And it's basically just grabbing it and putting it into this folder, and then it will go to upload. So once it's in that and it's uploaded, it's expected to be into the test upload folder where the algorithms classified diabetic and build a classifier will take that, classify it, and then produce a test output folder or file. The test output file will have a diabetes output.csv that will determine based on the patients entered. In our case, 10 patients were entered, and based on our training data and the data that we have explained in another section of this presentation, it'll provide us whether the patient has diabetes or not. And once this file is created, our UI section will cover how to actually present this data to the user. So in the chart data, we have a chart that will give us a ratio of machine learning results, where in our case 3 patients do not have diabetes, 7 patients with diabetes, and 10 total patients were submitted. And this was created through our Flash Python script on Heroku, where we'll take this output folder from our classifier and it will return our ML data return based on this location in this CSV file. Once it's JSON, it'll send it to our JS controller for JavaScript and presented to a meaningful chart. Thank you.
Hi, this is Ian. Let me introduce you the chart section of the application. The first chart is 5 active patients and type 1 and type 2 diabetes counts. We can see that we have 304 patients, with 46 has been diagnosed as diabetes. File data is used as training data in our application. The second chart is diabetes ratio of the machine learning results. This provides the visualization of the result of our machine learning classification. Thank you.
Hi, this is Lee. I work on the machine learning component of the project. The first thing I did was data extraction. In the FIRE database, we were given 300 patients and all of their observations. There are up to 41,000 observations, not all of which were numerical. Some observations contain strings with numerical data. Other times, it had even multiple numbers. To simplify the problem, as shown here, I used a mathematical trick called Cantor pairing to merge two numbers into one deterministic number. The result is shown here in my Excel file. I have 300 rows with each row representing data from every patient, and there's 168 columns for 168 types of unique observations. There's one final column that indicates if the patient is diabetic or not. You'll notice that there's a lot of missing values, and what I did was I replaced them with the mean of all the known data in each column. Next, I used Weka on this training set, and I found that ADA boosting with a decision tree was the best. It had a very low amount of error with cross-validation. This is most likely because there's some bias in the data. Patient diagnosed with diabetes were more likely to have performed similar lab tests. In future applications, given more data, it will be possible to rectify this.
Hi, my name is Nick. I also worked on the machine learning backend portion of our app. Initially, we wanted a model that would capture patient history that would allow us to predict at each point in time whether or not a patient was diabetic or at an increased risk of diabetes. This would have been either using a time series or recurrent neural net. Unfortunately, all the diabetic patients in the dataset were diagnosed prior to the beginning of observation data, so we only have a static view of diabetic and non-diabetic patients. We had 168 attributes in the raw data set. Some of these had very good coverage covering all of the patients, but many were very sparse. So we also filtered this to 17 likely attributes. You can see here, this included things such as glucose and BMI and weight. Here you can see the results for each of the training sets. Decision trees across the board took very little time to actually train, showing at 0.1, 0.6, or 0.75 seconds for any of them. The neural nets, on the other hand, took 2 minutes or so for the large attribute sets. The overall false negatives were very large for the smaller 17 attribute set, as you can see, which is not a very good result because this shows that a lot of diabetic patients aren't getting flagged to their doctors. On the other hand, if we got rid of the A1C test, which is essentially a diagnosis for diabetes, we do get a lot of false negatives as well compared to the full attribute data, which shows that a lot of our power is coming from the A1C test itself. This isn't a bad result, however, because there still is power when we don't include the A1C test, which helps the doctor find patients that are at risk that also have not had the A1C test. And once they've had the A1C test, our model becomes very strong at alerting the doctor towards accidentally overlooking a diabetic patient. In summary, we get very high-speed training results with decision trees and marginally better classification with neural nets. However, it takes significantly longer to train. The exact model to be chosen would have to be based on the production system demands and available hardware and how much data. In the future, we can transition from a classification model to a regression model, which would allow helping set provider-specific thresholds. An additional area in the future is to incorporate time information as we get more data. This would allow modeling patients as dynamic entities instead of static entities. This could enable additional alerts for change in risk, which would help a doctor focus on which patients need additional help to prevent full onset diabetes. And that's our project. Thanks from all of us.